So we have been discussing this multi-level gate circuit. Let me go through it very quickly. We discussed, uh, the possibility of redistributing a circuit into multiple stages instead of just two stage. And we started with the tree diagram concept. And then we saw how different approaches towards functional implementation, sum of product or product of sum, you can have different number of gate inputs, and reducing gate input is always good, right? And if you have multiple stages, that leads to increased delay. If you reduce the number of stages, that can reduce delay. But we also discussed in circuits, in certain scenarios, you may want to add delay versus reduce delay, right? So, it's not always a given that minimum delay is always helpful. And we'll see some examples hopefully today. Now, we also saw how to convert a basic AND OR circuit into other formats, and we highlighted the NAND and NOR specifically because they are typically the lowest area implementation of any logic. So if given a choice, we'll always go with NOR or NAND implementation. All right, and then we saw how to convert a given circuit into a NAND format as well as a NOR format, right? And that's where we basically spend most of our time in the last class discussing how to convert this circuit from AND OR to NOR or NAND. And I hope you try to practice it at home because I haven't received many questions. If I receive questions, then I know that, oh, this is where the confusion lies, right? Unless that happens, I don't really know whether you are confused or whether you got it. So please, if you haven't done already, practice at home and let me know how you feel about it, because these are important topics for your exam, midterm exam, or even quizzes. Okay, now, then we talked about using the K-map approach for multi-output circuit optimization. So imagine in a Boolean logic, you have, instead of one output, if you have multiple outputs, F1, F2, F3, and so on, right? And one example of that would be a simple adder circuit where you have sum and carry. So two outputs already. And we saw the first approach towards Boolean optimization would be to incorporate K-maps for these three outputs separately as if they don't talk to each other, and then come up with the Boolean output and implement the circuits that way. However, we also saw a quick example of some opportunities where you can share some components. Like for example, AB could be shared between two outputs, and you could have one common logic gate catering to the needs of two outputs. And that's how you could reduce the number of logic gates significantly, right? We also saw a clever trick of combining multiple outputs to come up with, for example, CD as one component. So obviously, this is a clever trick. When I explain it, it makes sense, I think. But how do you know that, hey, there are tricks available that you could, do something about it, right? It cannot be random. It cannot be fully manual. There has to be an algorithm. And that's what we are going to learn today, starting today, right? That's where we stopped actually in the last class. I told you that we will talk about coupling K-maps. So when you have multiple outputs, for example, the exact same example that we saw in the last slide, or maybe different. Let me see. Yeah, it's probably a different example. Yeah, it's a different example, but doesn't matter. We take a different example here. And what you do is you start with treating them as independent output. So you make a K-map out of this function, K-map out of the second function, K-map out of the third function. I hope by now you know how to make K-maps, right? Okay. Now, here is the difference. If I were to optimize the K-maps individually as if these functions don't talk to each other, as if they are not part of the same system, take a look at the one on the left. Okay. So I will give you two options. When you try to group the ones, will you prefer grouping these 4 ones together, or will you prefer doing it this way, like 2 and 2? Which one would you prefer, the first option or the second? Yes, I'm getting some answers, but don't feel shy to speak up. 4, right? More the merrier, as you know. And that is true. That doesn't change. Okay. Only in the only in the context of multi-output situation will you think otherwise. Let me show you why. We happen to notice, and obviously these examples are shaped that way so that it makes perfect sense. They fall in place, obviously. In real life, you may come up with a situation that doesn't really match up that well. But let's see. Notice if you select, instead of choosing these 4 ones in one group, if you select this group, you have a matching group in the second function. So if you create one logic gate or one component corresponding to this group, you could then share it amongst 2 functions. Does that 2 output? Does that make sense to you folks? All right. Notice one more thing. If you select this as a separate group, you can then share it with a matching group. You see that you have exactly matching groups here? Folks, how do you know that there are matching groups? Can anybody help me? Let's do this together, and I hope it will make sense. Can anybody help me figure out the functional expression corresponding to this group? What do not change here for these 2 ones? A and B. So can I write A prime B? But what else doesn't change? D. So A prime B D, right? What will be the expression for this guy? Exactly the same, of course, because it has to do with the location, not anything else, of course. So it's A prime BD. Now imagine if this is part of F1 and there are other terms as well, as you know, and this is part of F2, there are other terms as well. But there is one common term between F1 and F2, as you see, which I could share. You see that, folks? Does that make sense? Okay. Similarly, you can come up with a term corresponding to this group of 1, and you will see you could reshare it with the third function. So that's exactly what I'm telling you. Okay. You don't have to just do it completely manually. Here, we didn't have any K-map. We just happened to notice that, hey, AB could be shared between these 2 functional output, and that's how you reduced one gate. But what I'm telling you now is if you do K-map, the K-maps will give you hint as to what could be shared, right? So if you have matching groups, like this one matches with this one, and the other one matches with the other one, you know that they could be shared. Does that make sense, folks? Okay, one other thing is, let's see, that's not the end. For example, this one, this group could also be shared with this group. And the others, notice, the others cannot be shared. So it's fine. Whatever cannot be shared will have dedicated gates for them. But what can be shared, we can make sure to share them. We can make sure to group them in a way that it facilitates sharing. You might be wondering, okay, if we choose these 4 ones to group together, what will be the cost in terms of number of gates? Let me show you. Can anybody help me figure out the expression for this group 4 ones? What doesn't change here, folks? B doesn't change, and D doesn't change. Can I write this is BD? All right, this is BD. So you need a logic gate like this to incorporate BD for this functional output. You need a logic gate just for this group. Okay. When you get to the next function, what will you need to implement this one? Let me do it quickly. A prime B D. So you need another AND gate with A prime B D for this function. Are you paying attention? Are you with me? So to incorporate this group in a functional format, you need a logic gate. To incorporate the other group, you need another logic gate. So you need 2 logic gates already. However, if I could share these ones together, A prime BD, you would have used the one of the logic gates, which is A prime BD, and cater to the needs of both of them. You see my point there? So you reduce the logic gate. So that means when there are multiple functional outputs involved, if you just go for the minimum, like, the highest possible grouping or minimum functional output, minimum functional expression, it will not always give you the best solution because you'll miss out on sharing. As we teach the kids, sharing is good, right? So similar to that. Does that make sense, folks? So notice that it completely changes your perception towards design. you don't just go for the most optimized K-map output. You go for the most sharing. That is the important factor. So that's what I mean by coupling K-maps. So they, yes. Could you repeat that question? Sorry, I didn't hear you properly. So by the way, a good question. So first of all, when I said that you could share them, like for example, this one with this one, let me show you one more thing. This one with this one, that doesn't mean that is it. You have to account for whatever is not being shared. They will come separately. Let me do it properly. Okay, what else can be shared? Let me show you. This could be shared. So you have handled the ones that could be shared. What about the ones that cannot be shared? You also consider them. All you have to do is make sure you cover all the ones, but you cover them in a way that you have most possibility of sharing with multiple. Does that make sense? So I will not leave behind any groups of ones. For example, this one will be used, of course, but it cannot be shared. It's fine. We'll live with it. Similarly, this one cannot be shared with anybody. Sure. I see. For example, one option would be to group it this way and share it with this one. That is also a possibility, right? We'll see whether that leads to any benefit or not. If not, then we'll just leave it as is. Okay. Does that answer your question or no? Right? So first, and also, as you see, this is taken from from the textbook. They're trying to make a point. It's not a guarantee that they're giving you the most optimized result. For example, I just happened to notice that this could also be shared, but they are not showing that in the textbook. Maybe because they went ahead and tried it out and they saw it gives you diminishing return. So it doesn't change much. Sure, then you don't have to go through this mess. Okay. All right. But if you share, you typically get better result across 3 outputs or multiple outputs. Okay. So for example, after sharing, this is what you end up with. That's what the textbook says, and apparently you could share multiple components and eventually get better results. Let me show you. If you just go for independent optimization, take a look at this F1 versus the other F1. Which one looks simpler and more optimized? Which one? I mean, how can I, this is, say option X, this is option Y. Which option is appearing simpler? X, of course. I mean, we can visibly see that. How, and by the way, F2 appears, the same as this F2. F3 is exactly the same as this F3, right? Everything else remains the same except for F1, which looks more complicated. However, what it tells you, this dashes here, they represent that they're being shared. So A prime BD is being shared with this one. ABD is being shared with this one. AB prime C is being shared with the other one. So you're basically sharing multiple components. So notice, this is the fun part. So although you see them in the function, they're not really there in the hardware. They're basically gone. You see my point here, folks? Am I speaking to myself or are you still with me? Don't give up. I mean, if you need me to repeat, I will repeat. So notice this functional output looks more complicated because it has more terms. What I'm telling you is these terms have already been used. A prime BD is coming from this function. So you're not creating a new gate for A prime BD. You're sharing it. Similarly, ABD is coming from this function. So you're not creating it, you're sharing it. AB prime C prime is coming from this function. So you're just sharing it. So essentially, for F1, you just need one gate, which is this guy, to implement B prime C. As opposed to, if you go for this functional output, how many gates will you need? Yes, 1, 2, 3. So you need 2 more to implement this function, which looks simpler. But practically, if you think about the hardware implementation without sharing, that practically needs more gate. Right? And that's why you see, you save instead of 10 gates, you need 8 because you got rid of 2 gates by sharing. So it looks more complicated in functional form, but practically it is simpler. That is the big change here, folks, right? If it were just a function with one output, then no brainer. Go for the highest possible grouping of ones, you get the most optimized output. But in real life, most functions or many functions will have multiple outputs coupled together. It's not just one thing that is happening. So that's why you have to be mindful of this additional concept. Does that make more sense to you now? No. Okay. And I recommend don't just take it for the face value. And all of these are, results are given. Try going through this K-map yourself. Only then you will have more confidence, honestly. If you just listen to me and take my words blindly, it will not give you confidence. It will give you information probably. Oh, okay, we have to do it. But only when you try to do it yourself at home, then you'll realize, oh, that's what it means. That's what it means, right? So I want you to have that feeling. Please try this out. Don't just let it pass. Okay, okay, we'll just take it for the face value. All right, let's move on to the next slide. This is just another example, just a repeat of what we just discussed, right? And it will hopefully solidify the point. Let me show you. This is a K-map. This is another K-map for two functions, function 1 and function 2. So they are correlated. They are part of the same system. Now, if we just go for general grouping, right? If we go for general grouping, let's start with the ones that we would typically do, folks. We learned when we went through K-map, and I taught you myself, I told you this myself. If you see a 1 sitting alone somewhere, bring it inside a group. Don't let it sit alone, because that will optimize the overall output. Did I tell you that? Okay. So this is our approach. You take the biggest group with this 4 ones, and you see this one sitting here, you bring it with another group. Basically, you make a pair. You don't let it stay alone. And you try letting it sit alone and then see how the functional output looks like. It will never be most optimized. The more you group, the more optimization you can manage to get. That is true, still true for single output function. Remember that. Okay, how about this one? So you have 4 ones here. So you group them this way, and you had another one sitting right here. So you don't let it be, you just bring it under a group, and you repeat a 1. For example, this one is being repeated, which is fine. In the end, you will end up with more optimized functional output. So this is the typical solution that we will go for if we only do K-map optimization without considering the correlation, that these two functions are part of the same system. But now, okay, go through the process, calculate the number of gates, and you see how many gates you need. And now if you go through a different approach, instead of just blindly pairing the ones, I will look for opportunities to share. That is the new normal for us. So let's see. We notice that this one and the other one shares the same location. So when you convert it to a functional form, you could share the logic gate. Does that make sense? So instead of grouping it with anybody else, because if you group it this way, it's no longer be the same. It's no longer gonna be the same. But if you leave it alone, then you are gonna end up with a term for this one and the other one, and then you can share them. And after you share, you will see you have less number of gates. Although it should be less optimized in terms of functional form, but that was the point here. It looks less optimized, but practically in hardware, it is more optimized. Are you all with me so far? Okay, homework for you. I'm not gonna check it, but it's between you and yourself, right? Try to represent this in functional form and see how it looks like. Represent this in functional form, see how it looks like. Represent this grouping in functional form, see how it looks like, and then have a feel for whether that really makes sense to you. Okay, there are reasons why I'm not doing everything. I'm not showing you everything. Then you don't appreciate the fact, right? If you don't discover it yourself. Does that make sense, folks? Are you all with me? All right. Okay, so that concludes this particular lecture. I'm glad to be able to move to a new topic, because after a while, if we spend time on the same topic for a while, it becomes boring for students. So I become nervous as well. Right. But again, I'm more than happy to go back and answer questions if you have questions on any of them. So in this lecture, we'll talk about specifically timing and hazards in combinational circuits. Well, as you can see, we are getting more realistic, more practical with circuit design. when I teach you something, it feels like, oh, that's the end of the world. Oh, we figured it out. We figured out how to optimize Boolean logic using K-map. But then you see, oh, K-maps don't work beyond a certain number of variables. Okay, sure. We go learn a new approach. And then we see, oh, by the way, K-maps, whatever you learn for K-maps will not be applicable if you have multiple outputs. So we are kind of getting more serious and practical. I hope you see that. Now, in this lecture, we're going to be even more practical and talk about how the logic gates actually behave in real life scenario. They're not like idealistic software. Okay. When you try to code something, for example, if I give you a exercise that, hey, you have an AND gate, I provide an input 1 here and 1 here. What's going to be the output? You should say AND gate, both inputs are 1, the output should also be 1. Okay. Now, if I tell you that, say, if this one goes from 1 to 0, what happens to the output? When this one goes from 1 to 0, the output should go to 0, right? But the real answer is that depends. Wow. Okay, that basically contradicts what you learned so far, right? If you just look at truth table, oh wow, that makes sense. This becomes 0, so the output becomes 0 instantaneously. But that's not how real life works. And that's exactly what timing will tell you. Let me show you what I mean by that. The third slide will answer that situation where we have an AND gate. All right. So we are getting there. I just wanted to hit you with the reality that, oh, what you learn will no longer be true so easily. There will be yes, but. All right, let's see. So remember, logic gates are not like random software entities. They have hardware presence. So any hardware, no hardware basically works instantaneously. There is a delay involved. Everything takes some time, no matter how small, it will take some time to respond. And there are physical reasons behind it. And I can go deeper into the devices and circuits and explain the origin of that delay. Why it takes a microsecond versus the other one taking a nanosecond versus the other one taking a millisecond, right? There are serious physical reasoning behind the delay. But for this level of logic design abstraction, we will ignore the physical reason because you haven't taken VLSI course or semiconductor courses yet. They come from the material level responses. So there is a delay involved. So for now, we'll take it this way that every hardware has the specific delay associated with it. Okay, it could be 20 nanosecond to 20 microsecond or anything between. So imagine it is a CMOS inverter. You provide input 0, you expect an output 1 in terms of Boolean logic. You provide 1, you expect 0. However, practically, when you see the real life scenario, this is how it looks like. Let's take a closer look at it. Imagine your input was 0 for a while. So your output is 1, basically inverted, x and x prime. Looks nice and meaningful. But when you change the input from 0 to 1, notice for a period of time, which I can further zoom into, for a period of time, x prime doesn't change. It takes a while for output to respond and start behaving as it should. So it starts getting to 0 because the input gets to 1. But there is a delay. You see my point here? It is not instantaneous. In conventional scenario, we would consider that, hey, this is your input going from 0 to 1. Your output should go from 1 to 0 right away. But that's not the case. The case is you have a delay. You have a delay associated with the change. Yes. That's a great question. I'm really happy that you asked it. Otherwise, I would have skipped it. And you see, the more you ask, the more you learn. I'm really happy. So first of all, and by the way, I don't blame you. When I was a student, when my friends used to ask questions, I was like, come on, man, let us go home. Like, don't ask questions and he will talk more. I was like that, honestly. Like nobody wants to hear the professor talk more. But at some point, I mean, everybody gets to a situation where I wish I could learn more, something like that. So anyways, the reason is, I told you that you have a physical hardware for every component that we're using. How do you implement an inverter? You have an NMOS and you have a PMOS, okay? And there are two types of transistors. What you have in this terminal, so you provide the input in the gate terminal, you get the output from its drain terminal, okay? You don't have to know what gate and drain is for now. There are three terminals, actually 4 terminals in every transistor. Gate is one of them and drain is the other one, all right? So there is a capacitor connected to the gate, okay? MOSFET or transistors, they have capacitor, built-in capacitors connected to the gate, okay? When you apply a voltage to the capacitor, have you taken like the preliminary circuit course? You must have seen. How does the capacitor charge up? Does it charge linearly? Yes, there is a time constant involved, don't you think? There is a curve, like you gradually charge and you gradually discharge. You don't just charge linearly and discharge linearly, do you? No, because there is an exponential term involved, right? T over tau. Remember that time constant? So since you have a capacitor involved in the gate, and when I say that, hey, I go from 0 to 1, that basically represents a capacitor cannot instantaneously charge from 0 to 1, can it? There is a time constant involved. So that time constant means that you take some time to charge from 0 to 1. So going from 0 to 1 basically means charging up the capacitor at the gate. And going from 1 to 0 means discharging the capacitor at the gate. And charging and discharging the capacitors will have time constant involved. And that's why there will be this gradual change. This is how practical things work. Does that make sense? Okay. Thank you for the question. All right. So you see that there is a delay involved even in a simple CMOS inverter. And we will see how this delay could end up, oh, by the way, this is a nanosecond. This is an example of a nanosecond delay. And one other important point to keep in mind, folks, which I don't know whether it's visible here, but it will be visible hopefully in the coming slides. So when you go from 0 to 1 in an inverter, you have a certain delay. Let's consider that's epsilon 1. And when you go from 1 to 0, you have a different delay, which is epsilon 2. What I'm trying to get to, or this is also taken from textbook, what they're trying to portray here is that these two delays may not be the same. And they're practically, typically not the same. The time that it takes to change the input from 0 to 1 is not always the same to go the other way. Any guess why? You can make a mistake, it's fine. And I just basically hinted at it while trying to answer the previous question. Did I tell you that there is an NMOS here and there is a PMOS here? Did I tell you that? So there are two types of transistors involved, NMOS and PMOS. PMOS is connected to VDD, NMOS is connected to ground, and this is your input, this is your output. So when you go from 0 to 1 in the output, you basically discharge to ground. I'm sorry, what did I say? 0 to 1? So you charge. So when you go from 0 to 1, meaning you charge up the output, okay? So give me 1 second to clear it up. Oh, what am I doing? Trying to erase. Okay, forget it. Let me try to draw it again. So you have a PMOS and you have an NMOS. This is ground, this is VDD, this is input, this is output. When your output goes from 0 to 1, you basically charge it up. Now, tell me, when you're trying to charge a node, do you charge it from ground or do you charge it from the voltage supply? How do you charge? Do you charge it from ground? You charge it from, you must have done RLC circuits and simple, like when you show a capacitor discharging, where does the current go? To ground. And when you see something charging, where does the current come from? From the voltage source, battery or something like that, right? Does that ring a bell? Okay, so similarly, when the output charges up, the current should come from the VDD and it comes through the PMOS. But when it discharges, meaning when it goes from 1 to 0, for example, where will it discharge? Will it discharge to the voltage source? It will discharge to the lower voltage terminal, which is the ground, like right here. So it goes through NMOS. And fundamentally, there is structural difference between NMOS and PMOS. In terms of strength, NMOSes used to be stronger and PMOSes used to be weaker. So whenever there is an NMOS involved, the process is faster than the NMOSes. And people used to do some circuit design technique to make their strengths kind of match up with each other to some degree. Even then, you cannot have a perfect match. There will always be some asymmetry. So that's why there is a delay difference between low to high and high to low. Does that make sense, folks? To you or no? Okay, even if you don't care about this device level detail, just in that case, you have to take it for granted that, hey, the delays for one kind of switching is not the same for the other kind of switching. Okay, so that takes us to this slide, and let me explain that. So this is an input of a CMOS inverter, of an inverter circuit, and this is the output. Notice that there is a delay. How do you measure the delay? When I say 20 nanosecond, how do you measure the 20 nanoseconds? Let me tell you. So you start with the 50% point of the input. So this is the 50% point, like midpoint of the input. And you take the midpoint of the output, 50% point. The difference between these two times, this is the time axis. The x-axis shows time, right? The difference between them is called TP, stands for propagation delay. Okay, how long does it take to propagate the input to the output, essentially? And HL represents high to low. That is the output. The output is going from high level to a lower level. That's why TPHL. These are standard notations, by the way. You'll see them in data sheets, for example, right? So get used to this terminology. TPHL represents propagation delay for high to low switching of the output. And TPLH, as the name suggests, will be exactly the opposite. And they may not be the same, as you can see. This and this may not be the same. Depending on which one is stronger, NMOS or PMOS, you can have one less or more. All right. And how, when I ask you, what is the propagation delay of your CMOS inverter? How do you report that number? You basically take an average. Just take the two numbers and take an average. That's how you report the propagation delay. Does that make sense, folks? All right. All right. One more thing. So we covered the delay part, but there is another concept called slew rate. What is the slew rate? And this basically caters to the question that was asked before. Why do we see even the input? Forget about the output, which is being created by the inverter circuit. How about the input? I am providing the input. But remember, I am providing the input to the gate terminal of the transistors, which has a capacitor. So even if I want to or try to change the voltage instantaneously, it will not change instantaneously because I simply cannot change a capacitor voltage level instantaneously. No matter how fast, there will always be a time constant associated with it. So that's why there is this is called a rise time. How long does it take to increase the voltage from 0 to VDD? So it's called a rise time. And similarly, how long does it take to reduce the input voltage from VDD to 0? There is a time involved there as well. This rise time and fall time are important parameters, which you will also learn about. Rise time and fall time. Together, they are often called slew rate. This is a terminology that engineers like to use. Slew rate means rise time and fall time together. Does that make sense? Okay. And how do you measure that? It's shown here in this part. Notice. You look for 10% point up to 90% point of the transition, and you take the time difference between them. That's TR, rise time. And you take the fall time similarly, 90% to 10%. You have fall time. So slew, F stands for fall, R stands for rise. So rise time and fall time. These are standard notations that we always use. Remember that. And these are agreed upon standard, 10% to 90%. You cannot just change it to 20 and 80, right? This is engineering standard. Does that make sense? One final point, actually two final points. What is fan in and what is fan out? Fan in represents the number of inputs coming to a logic gate. For example, this logic gate has 1, 2, 3, 4, or maybe 5 inputs. So its fan in is 5, right? So when I say 2 input NAND gate, what is the fan in? 2 input NAND gate. I told you the answer. 2 inputs. So the fan in is 2. 4 input NAND gate, 4 fan in. So remember, fan in basically represents the number of inputs to a logic gate. And it may not be as obvious, like, okay, NAND gate is a standard gate, right? But you must have seen circuits where multiple outputs feed into one OR gate or something like that. What is the fan in of that OR gate? you can count the number of lines that are coming in to the input. And that's how you count the fan in. How about fan out? What you didn't see too much. You saw some, but I'm sure you haven't appreciated that. So imagine you have a logic gate and it is driving another logic gate here. And in addition to that, it is driving another logic gate. We have just finished discussing sharing. This is an example of sharing. You see that? You drive multiple gate with one gate. That only occurs when you share. If you don't share, if every gate drives a different gate, there is no sharing. So we have just finished learning about sharing. And now we have to talk about fan out, because fan out is only relevant when you share. When you share a logic gate with multiple other logic gates, that's when you use the same output in multiple times. So for this particular example, what is the fan out, folks? For this logic gate, what is the fan out? 2, exactly. It looks simple, like childish, of course, but these are extremely important metrics to keep in mind and to familiarize yourself. The fan out of a circuit determines the delay, because that we are talking about the timing diagrams here. So the delays are important. The more nodes or more gates you drive, the higher the delays. Let's try together. Okay, did I tell you that sharing is good? So imagine I give you an example where you have one logic gate shared across 3 sections versus the same logic gate shared across 10 sections. Which one sounds more optimized to you, folks? Sharing the same gate with 10 components versus 3 components. Which one is more optimized? 10? No, don't take the number for the sake of it. What do you really feel? Will 10 be more optimized in terms of area? If you don't share, how many logic gates will you need? 10. Don't you think? You have to provide 10 different inputs from 10 different logic gates if you don't share. For example, if you have like 10 childs, like somewhere playing together, you need to give them 10 different toys versus giving one toys that they're sharing and all playing together. You see my point here? Exactly the same situation. But remember, if you just stay with what we learned in the previous lecture that we just finished, you have an answer. Sharing with 10 components makes more sense. But what this lecture adds to the dynamics is that, okay, that means your fan out is 10 versus fan out 3. The higher the fan out, the higher the delay. The slower will be the operation. So can you live with this delay? And I'll show you the extent to which the delay changes the overall dynamics. I mean, the moment I get to the next slide, this slide, I hope it will make sense to you as to how that can impact the real life situation, right? But I'm telling you, delay is critical. And fan outs change the delay. Can anybody take a moment to try to answer why? Why fan out changes the delay? When one logic gate drives, say, 2 other versus 3 other, what changes? Yes, it is. Yes, partially it is correct. You are right, absolutely correct. But how? Yes, if you think about it, you have an output current that is being distributed, so you have less current in every branch. But how does that lead to delay? You are almost there. Yeah, so I kind of gave you the answer already. If you could relate it to something that I already told you. What is there at the gate? What is there at the gate, at every gate? Transistors. And what basically you're driving the gate of the transistor. What is there at the gate of the transistor? Capacitors. Did I tell you that? Capacitors. So when you see a line getting to an input, imagine it's as if you're driving capacitors. Okay, now if you all you're doing when you're driving something, you're basically charging up the gate capacitors. Now, when you have 3 branches, you have 1/3 the current. So you need almost triple, it's not linear, almost triple time, if not more, to charge up the same capacitor. Don't you think? Because the currents are getting distributed across multiple branches. So you need to provide current for longer. Are you guys all with me so far? It's as if like using like 3 hoses in one outlet, right? You're trying to water 3 different sections of your garden, but you don't simply have enough water. Like you need more time, honestly. So basically, if you branch out, you have less current flowing through the branches. So it will take you more time to charge up the capacitors in every branch. That means your delay for the overall operation will increase. Okay. Now, I'm excited to show you this one. Are you ready to see this? On your right, you see a diagram that shows what happens to different node voltages with time. X-axis is time, and in Y-axis you have different node voltages. These diagrams are called timing diagram. So this is an important aspect of circuit design or logic design. Timing diagram. We always compare different inputs side by side to see what makes sense and to identify problems. And I'll show you a couple of problems here. Number one, this is a made-up circuit, as you see, chosen in a way that will illustrate the point that I'm trying to make here. So imagine this is an AND gate, sorry, AND gate. This is an AND gate, and this is a NOR gate. Okay, so this input is 1, and this input is 0, set at 1 and 0. It's not changing. Remember, the concept of delay comes when something changes. If there is no change, if it is stable for a while, there is no delay to talk about because nothing is changing, right? So to make sure we could properly track the delay, we will keep one of the inputs fixed and we will only change the other one, right? If you change multiple inputs, you lose track of who is responsible for what. So in timing diagram, we typically try to change one thing at a time. That is just the norm in case you have a question later on. So, okay, so this is fixed. This is fixed. Only this input A is changing. See, I just changed one input. Okay, let's try to make sense of it now. When A is 0, B is 1, what should be the output of this AND gate? Quickly, let's do it quickly. 0? You guys all agree? If one of the inputs is 0, the AND gate will give you 0, right? Okay, so what is G1? This is G1 in the timing diagram. You see that it is 0? So it makes sense as long as A doesn't change. Oh, by the way, when this is 0 and the other this input is also 0. If this was an OR gate, what would be the output of the OR gate when both inputs are 0? 0 should be the output of the OR gate, but is it an OR gate? How do you know? Look at the bubble, it's a NOR gate. So the output should be 1. Okay, so that's what you see here. G2 is 1. So as long as A doesn't change, this is all nice and balanced and perfect. Okay, but the problem occurs when A changes. You see that A changes. Obviously, for the sake of simplicity, here we are not showing the practical rise time and fall time. Even if you assume that it literally just goes to high voltage instantaneously, for the sake of simplicity, let's assume that. Okay, it goes from 0 to VDD, high voltage, 1. Notice G1 doesn't change. Oh, by the way, should G1 change when A becomes 1? Your both inputs are 1 and 1. What should be the output, folks? This is an AND gate. What should be the output? Can anybody tell me? This is 1 now. This is also 1. The output should be 1. But notice G1 stays at 0. Why is that? Why is that? Yes, thank you. Did I tell you that there is a delay involved? Your outputs don't instantaneously change. They don't instantaneously respond to the input changes. Oh, input changed. I will change right away. No, there is a process involved. And interestingly, it all comes down to capacitors. Did I tell you that there are capacitors at the gate? Similarly, there are capacitors at the drain as well. So if you see a MOSFET, there is a lecture that I teach in 433. It's called, MOSFET capacitances. Basically, MOSFETs are full of capacitors. Gate, drain, like you name it, source, it's everywhere. So drain also has the capacitance. So the output is taken from the drain, and it takes some time to charge or discharge the drain capacitor as well. So the output doesn't respond. It takes some time to charge up the input, and then it takes more time to change the output. So that's why there is a delay. Even when the input changes, the output will take some time to change. So that's why meanwhile, G1 will stay where it was. It's like there is an inertia. It doesn't want to change. And then it starts responding to the input. And in this portion, this is a valid section. Do you see that, folks? But if you only look at this section, is this a valid logical argument, folks? Notice A is 1, your B is also 1, but G1 is 0. Doesn't that defy conventional logic? You see that, folks? So if you look at the truth table, this portion doesn't make sense. But that's what real life looks like. In a timing diagram, you cannot correlate. So if I ask you to work on the lab and you see, oh, it doesn't make sense. It's not working because of the delay. All right. So similarly, this delay is also propagated to the next stage. So the more stages you have, the more severe this situation becomes. All right. So we are out of time. We'll stop here and we'll pick it up from here in the next class. Thank you. Have a great weekend.